I want you to tell me which of these two lines is bigger one, larger one, or if they are same. What do you think? Same? How many of you say same? Okay, everyone. Some of those who don't say same, why do you say it? Say if I put a coordinate system here. Let's call the coordinates alpha 1 and alpha 2, and I say that this point has say A1 B1, this is A2 B2, this is A3 B3 and A4 B4, such that A1 equal to A3, A2 equal to A4, and this distance, or I should not say distance, but the coordinate difference is say delta B for both of them. Yeah. Is there any differing opinion that these lines have the same length?
Is it in 2D?
Yeah, this is in 2D, yes. Yes. Yeah, how many of you disagree or have a differing opinion that these lines are not of the same length? No, none of you? Okay, I'll draw another picture now. I'll erase the coordinate system here. Yeah. And draw something else. Now, what do you say? I wanted to draw a world map. That's the best I can draw. Now, yeah, I think I forgot something important. Greenland. Yeah. But now, okay. Now, how many of you say that these lines do not have the same length? Why? Yeah, if you already know, don't answer. Why? The difference in the coordinates is the same, and we have said that these endpoints are also same in one of the coordinates. Now, why is the length different? Why did your answer change? Okay, but say, this is not the. No, it's not about distance. I'm talking just distance. Forget displacement.
Are you talking about the projection of the map, and on that you have drawn these 2 points?
Yeah, this projection of it's a projection of the map.
And are you talking about actual distance?
Yeah, yes, actual distance, the one distance which one which shows on your Google map. Yeah. So now you might agree here that this distance was different than this distance, right? Because at this point for the red one, if alpha 1 was your theta and alpha 2 was your phi in the spherical coordinate system, then this distance was r sine theta delta b, right? 2 pi r sine theta delta b, and this was theta 1, theta 2, and the point was that this sine theta factor made the difference, right? Despite the differences in coordinates being the same. So yeah, the point which I want to drive is that even if the difference in the coordinates can be the same, the distance might depend on which point you start, and that is a fundamental difference of having like a flat space versus a curved space. So that idea is captured in a quantity called as the metric. How many of you have heard this word before, metric? Yeah. How many of you have seen this? ds squared equal to minus c squared dt squared plus dx squared plus dy squared plus dz squared, right? This is the Minkowski space for the flat world. How many of you have seen this? Okay, better question. How many of you have not seen this? Two of you, yeah. So, turns out, I mean, you must have seen this, right? Dx squared plus dy squared plus dz squared. Is this size legible to people at the back? Okay, fine. You have seen this, right? Now, turns out that, I mean, what is the special property of this kind of object? Dx squared plus dy squared plus dz squared. It remains the same even if you rotate your coordinate system, right? Right? Now, basically what we say, a fancy way to say this, that this ds squared is invariant under rotations. Now, there is something similar to rotations in when you have time as well, called Lorentz transformations. And in whatever frame you choose or whatever Lorentz transformation you choose, this quantity when you have space as well as time, minus c squared dt squared plus dx squared plus dy squared plus dz squared remains the same under Lorentz transformation. That is transformations of the special relativity. Yeah. So I hope that, I mean, you get the idea of this quantity. It is invariant. But the crucial point between these two figures, or even like say, forget this one. We can forget the special relativistic part here. Here, the difference was that this distance did not have, I mean, these coefficients were unity. It was like 1 times dx squared plus 1 times dy squared plus 1 times dz squared, right? So this kind of space would not allow for a characteristic or property like this, that it does not allow curvature, but I mean curvature, as far as I guess, you would not have seen something called as intrinsic curvature. The difference is that even if this was a 2D plane, and even if this was not embedded in a 3D plane, it can have something called as intrinsic curvature. So for an ant which was on this thing, it might happen that, you know, the space itself is 2D, there is no third dimension to talk of. The space can be actually 2D and there could be no third dimension, yet these distances can be different. I mean, nobody tells you that these two distances are the same, right? Right. Do people grasp this idea? How would you measure these distances? Physically speaking, how would you measure these distances as an experimentalist? As an experimentalist, how would you measure these two distances? What triangulation?
So we have like different stations, like all the way in between A1, B1, and B2.
Okay, yeah, that we can use. But then, how would you measure the differences, the distance between each small stations there? Good point. So yeah, so we can do something similar. A naive way to measure this would be the ink lost, right? We can say how much ink is lost, and if this turns out to be, the red ink turns out to be less in volume than the green ink, then we can say that red ink was smaller, right? So we can do similar experiments, and even if the space is 2D and there is no third dimension, we are forced to conclude that, I mean, this is not a flat space. It has intrinsic curvature. And yeah, that's what my point is. Now, okay, I want to come to the metric now, that if these coefficients are 1, then the distances between, say, x1, y1 and x2, y2, if this distance is delta x, then, I mean, the coordinate difference is delta x, then the distance would be just delta x, right? Right? ds squared would be delta x squared, right? Is this, are people following it? Yes. Now, instead of this, if we had some f of xy times dx squared plus g of xy times dy squared, what does this mean? Now, even if in this case, the coordinate difference could be delta x, say x1, y1 and x2, y1. Then what would be the physical distance measured? What do I mean by physical distance? Say for in this case the amount of ink lost or the time light takes to travel. So even if the coordinate difference was delta x, for example in our case it was delta theta or delta phi. Delta phi was kind of like x here, delta x. Even if delta x was same for both of these, the fact that it is multiplied by a function f of xy would mean that this distance was roughly f of x1 y1 times delta x squared, right? And now if you change x1 y1 keeping delta x constant, you will see that distance changes. Can you give me some examples of f of xy and g of xy in this case, in the world map case? Anyone? Are people getting what is the question? Any concrete example which you have already seen of f of xy with regards to this thing?
d theta square plus sin square theta
Yeah.
phi square.
So, yeah. Have you seen this quantity that what was it called? ds squared equal to r squared dr squared plus r squared d theta squared plus r squared sin squared theta d phi squared. Have you seen this for a spherical? Everybody has seen this, right? Now, do you see that, I mean, the fact that this distance is dependent on the initial position can be correlated to the fact that these coefficients of d phi and d theta depend on the position themselves now. They are not like constants, universal constant like 1 or 2. These coefficients depend on the point which your initial point was. And hence, if you wanted to find out the distance, what you would do was you would integrate ds squared. Distance would be integration of ds squared, right? Right? And it would, in general, say your coordinates was say r1 theta 1 phi 1 to r2 theta 2 phi 2. And it would be say for this kind of case f1 r1 or r theta phi dr d theta d phi in general, right? So this captures the idea that the distance element depends now on the coordinate itself, right? So this is the idea of the metric. Now you have seen these kind of metric, right? Turns out that for cosmology there is something called as the cosmological principle, which says that on large scales, as in large distance, the universe that we see around us is roughly isotropic. By isotropic, I mean that in whichever direction we see, the universe looks the same. And not only is it isotropic, it is also homogeneous, which means that if I am a year versus if I am a year, it should not matter. That's what it means by homogeneous universe. So there turns out there are only 3 types of geometries which are allowed by these 2 conditions or these 2 demands, that the universe be isotropic and homogeneous. And can you give one of them? What is a geometry that you feel that it is isotropic as well as homogeneous? A trivial one.
Normal Cartesian.
Yeah, exactly. Normal Cartesian, right? Normal Cartesian, in whichever direction you look, it's same. It's also same at all points. And yeah, another one could be a sphere. A sphere in 3 dimensions. A sphere embedded in 3 dimensions is also the same, right? If you are on the sphere, say if you are an ant on the sphere, then in whichever direction you look, it's the same. And it does not matter which point on the sphere you are. So that is another case of isotropic and homogeneous. And turns out, like, if you replace sphere by a hyperboloid, that also is same, although it's kind of harder to look at. So yeah, bolo, yes. Can you speak louder?
When you say the universe is astronomical, is there mass in the universe?
Is there?
Mass in
Yes, there is.
If we have mass in the universe, how do you ensure homogeneity?
I mean, okay, it depends on the scale of the universe. So I'm talking on the scales of roughly. Okay, good question. I'm talking roughly on the scales of like megaparsec, like thousands of lights here. So obviously, in our room, if I am standing here versus here, the universe is different, right? But if I am talking about scales of thousands of light years, then like what we see is that like it's like a fluid. Consider like a fluid. On if you zoom enough, then obviously there are atoms, right? And then those atoms, if you traverse a length scale of an atom, then you might, it depends on where you are, right? But if you zoom out enough, water is almost homogeneous. It does not matter where you are looking at, right? That's what I mean.
Like how did they come to the
Conclusion? It's observation. It's observation. We see that, I mean, one thing you can do if you have like, at your grandparents' place, if you have the old kind of TV, you can point the antenna at whichever position, and that the static which you get is actually the cosmic microwave background, and it does not depend on which direction you point out at. Homogeneity is a little bit harder to, I mean, experimentally verify at our scales, but yeah. Yes. So, is everything clear till now? So is there any doubt till this point? Yeah. So there are three kinds of possibilities that allow homogeneity and isotropicity. One is the usual flat space with the space part of the metric given by dx squared plus dy squared plus dz squared. As I said, there is another one called the spherical. Now the thing is, yeah, for S2, as in the sphere which has two dimensions, two coordinates, which is embedded inside R3, you could think of theta and phi, right? Or alternatively, you could have thought that this sphere was characterized by three coordinates x, y, z, restricted by this condition x squared plus y squared plus z squared equal to r squared, right? This was the condition of the sphere, equation of the sphere. Now, what you could do is, instead of this, you could, yeah, but this was sphere we having only two coordinates, right? There were only 2 degrees of freedom, right? Everybody gets this, right? But our universe, our universe has 3 degrees of freedom. Obviously, we can see it's up and down and z, up, down, bottom, and all 3 degrees of freedom. So, even if we want to do a spherical, it has to be in a sphere which we can kind of think as embedded inside 4 dimensions. So, the equation of the sphere would be x squared plus y squared plus z squared plus w squared equal to r squared. Now, there are 4 degrees of freedom initially, and this is one equation. It would restrict it to 4 minus 1, 3 degrees of freedom. And hence, if like we choose x, y, z as our free coordinates, then we can express w in terms of x, y, z. Yeah, w would be equal to square root of r squared minus x squared plus y squared plus z squared, and if we call this as r squared, then w would be r squared minus r squared. So, do you remember how we got to the metric of the S2 there, which is dr squared plus r squared d theta plus r squared sine squared theta d phi squared? We just had dx squared, where did it go? We use dx squared equal to dx squared plus dy squared plus dz squared, and express yeah, either like we can have one coordinates, express x equal to r sine theta cos phi, y equal to r sine theta sin phi, and z equal to r cos theta, and take the differential elements and you will get to this metric, right? Similarly, Now you can check that if we have this kind of thing, yes. So when the sphere is embedded inside 3 dimensions, you have 2 degrees of freedom, right? So if we want 3 degrees of freedom, we have to embed the sphere inside 4 dimensions, right? Yeah. If you are an ant on a sphere, you have only 2 degrees of freedom to choose, right? In R3, in typical sphere. But if you want 3 degrees, we obviously see that there are 3 degrees of spatial freedom for us. So it means that the sphere can be imagined as inside 4 dimensions. Yeah. Do you get this point? Yeah. So where was I? Now you can similarly characterize W equal to R cos chi, Z equal to R cos chi cos theta, X equal to R cos chi, sine, cos theta cos sine theta sine phi, and Y equal to R sin chi sin theta sin phi. If you squared all of these and add them, you will find that this is equal to R squared. Can you see that? Right? And now these has obviously 3 degrees of freedom, x, theta and phi. And now if you express dx, dy, take the differential element, it would be like r cos theta d chi sin theta cos phi, and do all of that. Express dx in terms of d chi d theta d phi. Then you will see that this metric, where did we have? If we had ds squared equal to dx squared plus dy squared plus dz squared plus d omega square. Use those relations to get a metric in terms of chi, and what we would have is this thing, r squared d chi squared plus sine squared chi times what we have there, which is d theta squared plus sine squared theta d phi squared. Is this all right? समझ में आया? I'll just erase this part. Do you understand what I have done? The calculations are kind of, you can take it as an exercise, but have you understand what I have done? It's literally the same thing. If you can see, this d theta squared plus sine squared theta d phi squared is just the 3 part of that point. So not only you can see that this part of the metric is sitting inside the bigger metric, which means that, I mean, we have the 2 sphere inside the 3 sphere, right? But yeah, this is the part of the metric. And the third type of geometry which allows homogeneity and isotropy is the opposite of that, hyperboloid. What we choose with, instead of this equation, we have x squared plus y squared plus z squared minus omega squared equal to r squared minus r squared, and we parameterize omega z x y z in a similar fashion. Now instead of using trigonometric functions, we use hypertrigonometric functions, and what we get is this. We can write r equal to, for this case, r, which is like r squared equal to x squared plus y squared plus z square equal to sin h chi, r times sin h chi, and w equal to r times cos h chi. And if you know what these functions are, then you have r squared minus omega squared equal to r squared sin h squared minus cos h squared, which is r squared times minus 1, which is minus r squared. So this kind of parameterization we can use, and what we get for this kind of metric is this: r squared d chi squared plus sin h squared chi d theta squared plus sin squared theta d phi squared. Right? Any doubt, any confusion till now? If there is, please tell. I mean, you might have seen the hypertrigonometric function for the first time, although these are common in Lorentz transformations. Doubt है कुछ? नहीं? Okay. Okay, हाँ, okay. You mean this? Good question. I think this would, yeah, so we want x, y, z to be isotropic, right? If we choose, you could have instead this is also allowed, it's just a different signature, but we want the signs, relative signs between x, y, z to be same, because we see isotropicity, right? So whichever direction, there is no preferred direction between x, y, z. So that's why the coefficients of x, y, z in this equation need to be same.
It is homogeneous in space and in time, right? And isotropic.
No, it is not homogeneous in time.
Only in space.
Yeah, obviously, I mean, if it was homogeneous in time, then there is nothing to study. Yeah. Yes, I mean, hyperboloid, like, which is hyperboloid, which is embedded in R4, H3. It's isotropic in the first two dimensions then. Yeah. I mean, if you calculate the curvature tensor, if you, I mean, do it rigorously in GR, you would know how to calculate the curvature, intrinsic curvature of a figure. Then, yeah, curvature is the same. Yeah, it's a fact of GR. I mean, if you are confused about it, you can just take it as face value. That, yeah. Yeah. So, yeah, this is. I mean, this is one way of parameterizing. Another way is like you can solve for W and eliminate W from this. For example, for the sphere case, yeah, W was equal to square root of r squared minus r squared, right, for the spherical case, isn't it? And then we can substitute what is dW. dW would be just minus r dr by r square minus r squared, right? Right? And then we can substitute this back into the metric. So we had one form where we had expressed in terms of chi, theta, phi. Another way would be to express the same thing as r squared by r squared minus r squared dr squared plus r squared d theta squared plus sin squared theta d phi squared. Now we keep, instead of like chi, theta and phi, we keep r, theta and phi, where r is given as x squared plus y squared plus z squared, but if you add all of these, it's just r sin chi. So we can use this transformation. And why I am doing that? Because for this case, for the hyperboloid case, you can write W equal to square root of r squared plus r squared. Then dW would be r dr by square root r squared plus small r squared. Is this visible? I hope. And what you would get after substituting it is this thing. d phi square. Yeah. We can substitute chi and r, where now the small r radius of the sphere is given by capital R sine h phi. Note that capital R is just a parameter, it's a fixed value. We are not changing that. Okay, yeah. Any doubt till now? No? Then we can combine all these three into one single equation given by ds squared equal to dr squared by 1 minus k r squared by r squared plus r squared. I will just write d omega 2 squared, where omega 2 is just this element. Is that fine? And k, here k equal to 0 means flat space, k equal to plus 1 means spherical or S3, and k equal to minus 1 means hyperboloid or H3. Yeah. So this is the metric which we will be using, an important metric. And okay, this is not quite the metric. Now we obviously need to incorporate time, because as we know in special relativity there is component of time, and the invariant is not just the length in the space time, but rather length, the invariant length under Lorentz transformation, which is given by just add a minus c squared d square. So I'll just write it here. dt squared. Yeah. So this is famously the FLRW metric. Is that fine? Yeah. Now you forgot to ask one important question. What is that?
What happens if Q is not an integer?
Oh, I mean, no. The thing is that we are, I mean, it's just case study, just to make all of these three compact into one equation. It's just k equal to 0 is flat. Yeah, it's just like instead of writing for flat, this is dr squared. For spherical, it is dr squared by 1 minus r squared by r squared. Instead of writing these separately, I have just written it into a one equation. I think, is there a square root? Yeah. Yeah, you have forgot to ask one important question here. I mean, why are we doing this? Why are we concerned about metric at all in the first place? What does metric do? Why would we consider metric as an object to study? Huh? Yeah, okay, fine, curvature of the space. So this bottle is curved. Why I am interested in the curvature of the space? So the thing is that what was I going to say? The thing is that metric determines how particles move, how objects move in the space time. So you must have heard the Fermat's principle of least action, right? That light travels the minimum time. So similar thing applies to particles, that particles reduce this action of minus ds squared. They move in a path such that the integral over the path of minus ds squared is minimized. So that's why we care about the metric in the first place. Is that okay? Yeah. And this metric as of now obviously if you see this metric, then there is no explicit time dependence, which is kind of strange, right? I mean, it does not evolve with time. Tomorrow it would be same, like yesterday it would have been the same. Thing is, I have written it kind of wrong. This is metric as of today. In general, what happens is that you might have heard this, that the universe is expanding from pop science videos, and the scale of expansion, so this part, it is captured, the factor by which it is expanded is called, it's captured by the obviously sounding name called scale factor, which is called A of t. And this is the actual FLRW metric. Minus c squared dt squared plus a squared. Yeah, so A of t captures how big the scale is. For example, tomorrow, if Earth was this much, tomorrow Earth is this much, and day after tomorrow it would be this much. So the coordinates of this point, theta comma phi, would still be the same, but the distance between these 2 points, theta 1 phi 1, theta 2 phi 2, theta 2 phi 2, obviously this factor has changed, right? The coordinates of these points are same, but the distance between these 2 points have changed. Similarly, this A of t captures the dependence of time dependence of this metric, and the whole game is about finding what A of t is. If you know A of t as a functional form, explicit form of A of t, then the game is solved, right? Right? People appreciate this. We know the metric, and hence we know how particles move on that metric by the minimization of this action. And yeah, one more comment here, that this metric has kind of a scale invariance. What do I mean by that? Should I erase this part? I'll erase that part. If A goes to lambda A of t goes to lambda times A of t, R of t goes to, hang on, I think I wrote it wrong, 1 by lambda. Small r of t goes to if you do this transformation, then you can see that the metric is invariant. The form of the metric would remain the same. Do you see that? Multiply A by 1 by lambda and R, capital R and small r by lambda, then you will see that these lambda cancel out, and hence, if this is true for all lambda, hence we can choose a lambda such that A of t naught, where t naught is now the present time, is 1. Do you get this point? We can choose a lambda such that A of t naught is now 1. If it is not 1, just divide it by that quantity to get this. Yeah, so this is the FLRW metric. Any doubt till now? No? Yeah. Now obviously we are interested in, like, the whole game started with what is the distance between 2 points, and then we are now in a position to calculate what is the distance between 2 points given this metric. And this is the form. If we start at origin, which is like r equal to 0, to say r equal to r naught, theta naught, phi naught, then we just integrate this ds squared, square root ds, square root minus ds squared through the straight line joining these 2 points, what we would see is that we would get this term at constant time. Obviously, if I want the distance between this point to this point, I should freeze time and calculate it, because that thing itself might be moving, right? If I want to calculate distance with chalk to that mobile, then if the chalk is moving, then I should first freeze time. So at same constant time, I should evaluate this, and if you just substitute it, what you would get is the distance d is integral dr by square root 1 minus k r squared by r squared. Is this fine? Right? Sorry, what? Why are we not integrating for?
Is it minus
Minus, yeah, sorry, I'm using a different thing here. Sometimes in QFT they would say put plus here and minus here. Yeah, we should integrate plus ds squared. Sorry. Yeah. Good catch. And you would get this form. And this is called the distance between the origin to this coordinate. Now, as you can see, obviously, it makes sense why we called it as the scale factor, because even if r0 is fixed, so this integration is from 0 to r0, even if r0 is fixed, as time moves, the scale factor changes, and hence the physical distance between 2 points would change as per the evolution of a of t. Now, yeah. Okay. So if we have the coordinates, we call this distance as d physical. I'll tell you why I have put this subscript physical. The thing is that our points henceforth would be categorized not in terms of physical distances, but rather the coordinate itself. For example, in this case it was theta phi there. So instead of using actual distances to mark them, we'll use the coordinates. And as we can see, although the coordinates can be fixed, the distance can differ depending on the scale factor and evolution of the scale factor. So we'll say that our coordinates will be given by x, and the physical distance would be given by x physical, right? And they would be related by this a of t times x of t, right? It's like that, the expanding earth which I have shown. X of t would be just theta phi, a of t would capture the expansion. Now if you want to know the change in distance or change in the position of the physical coordinates, we'll do this. Dx physical by dt would be d a dot. Everyone understands this dot notation, right? It's just derivative of time times x of t plus a of t x of t, x dot of t. Now this we can divide by a of t, multiply by a of t, and what we get is this quantity a of t by a dot of t by a of t is called the Hubble parameter. And as we can see, a of t times x of t is x physical plus let me see the notation here. This is called the peculiar velocity. The way to understand this is that this part says that even if the coordinates do not change, the velocity has non-zero component, and on top of that the velocity might change. So for example, you might have seen in pop science videos that a balloon expanding like this, and this is literally the balloon, and if a cat is walking or a human is walking, then its speed would have two components, one due to the expansion of balloon and another due to the fact that the man itself is walking on the balloon. So this peculiar velocity is kind of like man walking on the balloon, and this is due to the expansion of the balloon itself. Yeah, and this is kind of the way we measure the Hubble constant as well. We just plot, assuming that V peculiar is small, we can plot x physical or the distance versus the velocity of different galaxies that we see in the universe. And what you would find that galaxies are distributed something like this. And that's how the Hubble was the guy who found this, empirically found that the distance or the velocity of the galaxy which is receding away from us is proportional to the distance. So yeah, it's named after him and it's called the Hubble parameter. And the Hubble constant, as they say it, is just Hubble value of Hubble parameter right now. Yeah, I mean some comments about h of t. We say that h of t or h of t naught, as in now, it's roughly 70 kilometer per second per megaparsec. As you can see, it has units of inverse of time. So what it means that if a galaxy is 1 megaparsec away, it recedes roughly at 70 kilometer per second. Now there is a unsolved problem in cosmology called the Hubble tension. This is just the average value. Two different measurements have been taken to measure h, two different types of measurements rather, one from supernovae and one from I guess the CMB, cosmic microwave background. One of them is at 67 plus minus 0.5 and other one is at 73 plus minus I guess 1. You check the error bars. The point is that these values are sufficiently far away from, and even if you consider the error bars, they are, I mean, quite far away, and this is called the Hubble tension. It's not solved as of now. Yeah. Okay. I'll take redshift. Any doubt till now? Why do we have? What? Oh, different values. I mean, that's the whole question, right? People don't know why do we have. It's like different types of measurements. It's same as your physics lab. You get some different value, the other lab gets some different value, and unfortunately we cannot force the data here. No, not that I know. Huh.
I think I've read somebody suggest that if you consider the rotation of the universe, then the value is not.
It could be. I have no idea. Share the paper on the, maybe on the group or to me on Teams. But the rotation of the universe would fundamentally violate the isotropy, which is fine. Again, isotropy was just a empirically found formula. But if the universe rotates, then it means that there is a rotation axis, right? And then there is a preferential direction. But yeah, I mean, we can talk about that later. Yeah. So we have this metric. Now, I mean, some of you might know that the equation of motion of light is given such that ds squared is 0. This is the, I mean, light follows this equation of motion, which from that you can immediately see it means c squared dt squared, or I'll just remove the square, c dt is plus minus square root of a of t dr, assuming that, I mean, it's moving in radial direction only, then it's given by this formula. Yeah. This is the equation of motion for light. And why are we interested in this? We'll come to something called as redshift, which is like, if you attend any of cosmological talks, they would talk in terms of not of A of t, but rather redshifts. Yeah. So suppose like there is a galaxy at distance r1 and it emits this is not distance, this is the coordinate, by the way, sorry. There is a difference between distance and coordinate. This is the coordinate r and it emits a wave at time t0. So how much time would it take to reach us? It would be say t1, and the t1 would be given by integral c dt from say t0 till t1 equal to, since it's moving towards us, it will have a minus sign, e of t would be here, yeah, 0 to r to 0 dr 1 square root 1 minus k r squared by r squared, right? Now, I mean, say the crest was emitted at t0, a waveform has a crest, right? This was emitted at t0 and this was emitted at t0 plus delta t0. Then similarly we can write this equation, right? t0 plus delta t0, and that the other, I mean the second crest would arrive at say time t1 plus delta t1, right? And it would still follow this equation of motion, right? Any doubt till now? Okay. So t1 is the arrival time, which we yet don't know. Delta t1 is the shift in the arrival time, and if we compare these two equations, we can see immediately that dt by a of t, t0, t1, subtract these two equations, minus t0 plus delta t0, t1 plus delta t1, dt by a of t equal to 0, which means, what do we get? Since delta t0 and delta t1 are very small, I mean, consider this as a galaxy. So this difference between t0 and t1 would be in orders of light years, while this is just the time period of the particular wave, electromagnetic wave, which is in like nanoseconds. So we can just take, I mean this is very small, so we can just subtract the things directly, and what we will get is that 1 by a of t at t0, let me check whether, yeah, not 1 by a of t, delta t0 by a of t, we'll get this, or rather, to put it more cleanly, t1 a of t1 by e of t0. So what is the did I make some mistake? Sorry. What is the interpretation of this equation? Can someone tell me? Is this legible first of all to people at the back? What is the interpretation of this equation? How do you interpret? What does this equation say? Any guesses? Any guesses? What does this equation say? You can sit here if you want.
The time experienced at T1 and the time experienced at T2 scale.
X. What do you mean by experience? There is no experience here.
Like the flight time.
No, flight time was just difference between t0, t1 minus t0. Delta t1 is different, as I said. Okay. Any other guesses? Free feel to speak. Yes. क्या हुआ? Yeah. Any? No one? What? Just see what these quantities are. What does delta t1 mean? Okay, so the delta t naught by definition is the time period of the wave which was emitted at this galaxy, at this point, right? This is some galaxy, and we are here at say r equal to 0 origin, right? Now it gets to us this point in the wave function, I mean the signal gets to us at t1, and then at some t naught, I mean, okay, I'll show it by say 1 and crest number 2. This was emitted, correct, but I mean that's true, but it's talking in terms of time period, huh?
Measuring the time period of the oscillation.
Yeah. So delta t1 is the time, delta t naught was the time period at the position of galaxy, the galaxy which was far away. Delta t1 is the difference between number 2 minus number 1, the time of arrival between number 2 minus number 1, which is again the time period of the oscillation as received to us. So it says that a of t1, a of t0. Obviously, t1 is greater than t0, right? The signal cannot arrive before it has started. And if we assume that a of t is monotonically increasing, which we will see, we have good reasons, then it means that delta t1 is greater than delta t naught, which means time period has increased. Wait, how does that make sense? t1 greater than t naught. Yeah. So time period has increased. Yeah, it's called the cosmological Doppler effect, but it has nothing to do with change. I mean, it has, you can think it of in its way that it is galaxy is receding away, but even if the galaxy is fixed at the coordinate r, the keyword is coordinate, not the distance. The galaxy would move away from us, but even if it is fixed away from coordinate r, it would still move. And why I am not calling the usual Doppler effect? Because if you see this, even if you ignore the peculiar velocity, the speed, the physical speed, is linear with x physical. So if x physical is much large, then this physical velocity can be greater than speed of light. Does that make sense?
Change this distance is due to the change in time coordinates.
What?
Like if the coordinates remain the same.
The physical spatial coordinates.
Remain the same, then
Yeah.
the distance is changing with the time coordinate.
Yeah, I mean, to be more precise, it changes due to the scale factor. The scale factor is increasing. Yeah, expansion is increasing. Yeah.
So this time factor is defining this expansion factor is defining this Doppler effect.
True. If there was no expansion, as you can see, this would cancel out, delta t1 equal to delta t0.
It is not due to the coordinate expansion.
Yeah, it's not due to coordinate expansion. The coordinate is same. The galaxy would, for us, it would see, we would appear, it would appear that it is moving away, but the coordinate is fixed, as I saw in the bubble diagram which I gave. The coordinate is fixed, and we can relate it to the wavelength, delta t1.
Cartesian plane is expanding itself, so the coordinates remain the same.
Yeah, that's a good way to analyze it. Exactly, expansion of user. But the key point is that it is not the Doppler effect which we see from the velocity of light moving, relativistic movement, because you see that this speed, even if you ignore peculiar velocity, it is linearly with time. So as I showed you on that graph which Hubble had plotted, the graph was that distance versus the velocity which you observe was linear. So obviously there would be some point C, which would mean that there would be some galaxies which are receding farther than speed of light. And obviously then, if it was just the velocity part, if the redshift was coming from velocity, then it would have been infinitely compressed, or to be more specific, negatively compressed, or imaginarily compressed. I don't know what that means. But obviously it's not the case. It is different from the cosmological redshift is different from the Doppler redshift. Yeah, and yes?
When we put A of t or a square of t in terms of space rather than putting that as a scale factor for time, is there a physical reason for that?
You mean you can do this? You wanted to do this?
minus c square dt to the e as exactly.
Yeah, that's an excellent question. We could have done that, but as we will see, it does not affect the physics much, in the sense that, I mean, there is something called as conformal time that we will see, and I mean the main physics of it is given in terms of conformal time, and I mean the scale factors of the metric do not depend that much. Yeah.
You said that redshift induced by acceleration, or in this case, the change of speed is not equivalent to the operator, or relatively the operator that you obtain.
Yeah, the normal which you do in
Why
yeah.
is that so?
Because I mean you can see, if it was, as I said, the speed of galaxies was more than c. If you remember the Doppler shift formula, then the delta lambda or the lambda prime was given by v plus c by v minus c. Now if v minus c is negative, that is v is greater than time, greater than c, then this would be imaginary, right? So it's not due to, my point is that it's not due to the fact that, I mean, you cannot just say that the galaxy is moving away and hence we are seeing that. You cannot substitute v equal to, h times d in this formula. That's what I mean. Yeah, this is what I mean. You cannot just say blindly substitute v equal to h times d in this formula.
You obtain a phase difference of pi instead of the great elevation.
That might be true, but I mean, my point was not that. My point was that this v that you substitute, it's not h plus d. These would give different results. It's not like you can just blindly substitute that the galaxy is moving at speed v and hence we can put that formula.
While giving the coordinate, first absolute coordinates do not exist in the relative. So we can assert any coordinate system in relative sense. If relativity has to work, then both can be in an equivalent picture.
Okay. Do you mean special relativity has to work? No. This framework is independent. I mean, special relativity does not work here. It's yeah, because as you see, I mean, this incorporates homogeneity, right? Now, if in my rest frame, if the space is homogeneous around me, if I start walking towards this side, I would see my front would be more compressed than the back, and hence homogeneity would be violated. So homogeneity, by demanding homogeneity, you demand that there is a particular rest frame, and that's fine. I mean, general relativity, if you would go on to study, does not demand that special relativity to hold at non-local times or non-local things.
Redshift light or the Doppler shift light would change if you move forward, but the length contraction would remain the same axis.
Okay, but I mean that violates homogeneity, right? My point is that special relativity need not work in general, and that's why you have general relativity, right? The word special is there for a reason. When things get non-local, then special relativity no longer works. As you can see, the speed of light, there are galaxies which are exceeding speed of light in our frame. I mean, that's fine. You can ask me later or on Teams if you have any doubt. In fact, even in flat spacetime, you can show that if you are accelerating, this is one question which I posted in decoherence, I guess, that even in flat spacetime, you can show that speed of light is not constant. You can get back on me on how to prove that. There are certain special frames in which you can show that speed of light is not constant. Anyways, that's a different story altogether. Speed of light, the physical speed of light, speed of the photon. But anyways, that's a different story altogether. I'll come back to here. We know lambda is in the wavelength, is proportional to dt, right? Wavelength is proportional to time period. and hence we get what we call as redshift. Z is equal to lambda received, lambda emitted, I mean the wavelength of the light which was emitted by the galaxy minus wavelength received by wavelength received. And if you put in the math here, it's just okay. A of t naught can be replaced by 1 because, as we say, t naught is considered now, and hence we can call it as 1, and we'll get this formula that it is 1 by a of t1 minus 1, or z plus 1 equal to 1 by a of t. So this is the redshift. This is very important formula. You might, if you are taking notes, you can take this note. And what people talk is not in terms of a of t but z. So when they say some event happened at redshift z, so for example they would say that Big Bang nucleus synthesis happened at redshift of 4 into 10 power 8. They mean that it happened at a of t such that the redshift corresponding to it was 4 into 10 power 8. Do people get this?
Like they consider A1 to be that A0 to be the beginning of the universe, or now?
No, now a of t0 is always now. It is always now.
How can they get that A of t at the beginning of the time?
That we will, okay, beginning of the universe is defined to be 0. If we believe Big Bang means, yeah. The question, how do we get t, is that's a model dependent. I mean, we might go into the second lecture for this, or maybe, I don't know, maybe today if you allows me. But yeah, that's a different story. We are not considering dynamics here. We are not studying evolution of A of t. We are just talking about this structure. The very fact that we have the metric like this, what does it mean? So whenever you will see papers or go on some talks on cosmology, what they would say is that A of t, instead of talking like what t they talk, they first of all skip what t they are talking about. They talk in terms of A of t, but not only that, they talk in terms of the redshift z. So z, you can get A of t from here. A of t is 1 by z plus 1, right? So if they say redshift 3000 or 3400, it means that they are talking about the time. So redshift is a proxy for time. It means that they are talking of the time t such that A of t was 1 by 3400 plus 1. So you solve for this type and then they are talking about that time. Is that clear? Can we take half an hour more? Or क्या हुआ? Yeah, audience, it's up to audience. It's
How many of you are saturated?
yeah, please tell honestly. Please tell honestly. Don't hesitate.
If you are saturated or not understanding, it's no point.
Yeah, completely.
If you are saturated, please raise your hands.
You fourth year, you can go out. Yeah, genuinely, if you, I mean, you already know this. There is no point in. Yeah. If you want, you can go out. Yeah. Yeah, please be honest. There is no.
One thing, we can stop the session here. If you want, we can summarize what we have discussed today, and if people have doubts, we can discuss that. To fill in the gaps we have in today's lecture. Is that fine? I think it works for everyone. So I think we can do it.
Hang on. Yeah, there are few things, like 15 minutes, can I take? 15 minutes? Okay. We'll talk about the size, and this is important concept, you can note this down. We'll talk about the size of the universe. I mean, people say that it's like how many, 90 billion light years in distance. How do we know that? Now it's trivial from here. Where did it go? Yeah, the distance, this formula. If you just use this and yeah, so you have this formula, physical time, and we talk in terms of light, so you can replace this integral by this. So what I will do is, you just replace this integral with this, and we'll get d equal to a of t times 0 to r max of t. So we want to know if at all there is a maximum distance to which we can see. It might be infinite. You replace that thing with the speed of light, equation of motion of light, and you get this thing. Did I miss something? Yeah, obviously factor c. This is units of time. Yeah. So what does it say? It says that, obviously it's a function of time. You start at the origin and look out, you calculate this value. So r max of t, say you fix t equal to now, you calculate this integral for time t.
From which respect are we calculating the R max?
Okay, R max is what you want to find out. R max is unknown here. R max is what you want to find out.
ET is now.
T R max is a function of t. So let me put it as like t is what we know, and the form of at is what we know. And if you do this integral, obviously this is wrong. This is t naught. Yeah, so the point is we want to calculate what distance the light has traveled from 0 till now. From the Big Bang till now, what distance has light traveled? And it is would be given by this, right? This expression. So what this tells is the distance light has traveled from the Big Bang till now. And obviously, as you can see, if it depends on what form a of t is, and this value, if a of t is say t squared, for example, say, then this diverges at this integral diverges near 0, right? So it might happen if a of t goes as t power n, where n is greater than 1, then this value diverges, which means that the universe would be infinite. The length of the universe now would be infinite, right? But we know the observable universe is how many? 90 billion years across, billion light years across, which means that there is a certain form of a of t that we can get, and we will calculate this next time. Yeah. This. What is the actual value of
n, like t power n?
T power n. Oh, it depends on which model we are taking. So currently we are in matter dominated era. So matter dominated era n is 2/3. Right? I think. Yeah, it's not divergent, and hence it was not. But the crucial point was that in the radiation dominated era, like I'll talk about what radiation and matter dominated era are, the n was half. Still it was not divergent.
The rate of expansion changes.
Rate of expansion changes. So if there is too much matter, matter behaves differently, radiation behaves differently. So they influence how a of t changes. We'll come to the dynamics in the next lecture, and that's what this is. Yeah.
Like when matter was in the form of pure energy at the beginning.
Yeah, radiation, just photons, and yeah, that's what it is. And this is called the particle horizon. This concept is called particle horizon. Yeah, and we have something similar to event horizon, which is that, if I draw in terms of, so this was till Big Bang till now. So yeah, this distance tells the scale size of universe. So if we talk in terms of time, this was Big Bang, and how much distance in light terms of light one. You have seen the concept of light one, right? What distances in the past could affect till now. So this is time, this is distance, say for example. What distance till from past could affect now. This is the size of the universe that we see. Now you can do the similar thing in future. So if we start at now and emit light in all directions, at infinity, at time t equal to infinity, would there be a similar restriction on size? So this is d particle, d event horizon is that if you start at t naught equal to now and send light to infinity, then what is the maximum distance they can cover? And this is given as a of t. Now t0. Yeah.
So at that point, like the phase change from energy, like radiation to matter, dominant.
We are currently in matter dominated.
It can happen that the universe changes from matter to something else at such a rate.
Crucially, yeah, that's what we'll see. Good catch. We'll see that it changes to something called as dark energy, and yeah, t infinity. Yeah. Do you get this event horizon concept? So, if a of t, if you substitute this value, where was it? Half. Then the area under the integral, what is it? It also diverges, right? But if a of t was exponential, so as we will see, a of t was like say exponential lambda times t, then this is convergent, more importantly, which, sorry, no, it's not you. Yeah. It's convergent if a of t was lambda times t, e power lambda times this, it means that convergent. So if even if you send out light rays now, there would be maximum distance that they can reach, and that is called the event horizon. Yeah, and I mean Schrodinger had this comment that where did it go? Like even if two friends are sitting together, they would eventually drift apart by the expansion of universe, that they would never be in causal contact after some time. But yeah, and now I mean this is the last physical concept. I'll introduce a mathematical concept called conformal time, tau, which is just like it's a function of time given by this 0 to t.
Can we introduce new mathematics in the next?
No, it is just one definition. One definition. Yeah, this is it. We see that this factors appears too common, and hence we call it as tau. And the nice thing about tau is that light rays travel, if you introduce the chi, this is the exercise. If you introduce chi and tau, light rays travel in 45 degrees. So in Minkowski space you had 45-degree light rays, right? But obviously due to that metric, these light rays would travel very weirdly given this equation. What is this? So it would have some kind of behavior in tau and chi, or maybe some r. But that thing makes it so such that light rays travel at 45 degree in chi tau plane. So you can just construct diamonds. Yeah, and that's it for today. One exercise which I would want to give you, take this metric, or not this one, the metric in terms of chi, theta and phi, and find out, I mean prove this fact that light rays travel in 45 degrees, which means that it must.
This graph that you draw, 40 degree, if you know the phi value, then we get the tau.
No, that's not what I mean. I mean, it's, have you seen the, yeah, for a light ray, yes, but I mean, usual in Minkowski space, yeah, that's the lecture. The lecture ends here. I mean, you can take it as a small exercise that use tau and chi and these kinds of formulae, not this one, those one. Yeah, c equal to 1, yes, obviously, yeah, 45 degree angle in c equal to 1. I mean, they would be say almost the same as Minkowski, and I would encourage you what it means by almost, and it is related to what you had asked. That why didn't you put a of t here? Kind of related. You can. It's not that difficult of a maths. You can have a look at Tong. I am following Tong's lectures, David Tong's lectures notes. Yeah. And what was your question? Your question, huh?
If you know the value of pi, then you can
Yeah, if you know the initial condition and the direction, then you can figure out. It's like just the Minkowski space. In flat space-time, you have Ct and x. They are independent coordinates, obviously, but if you know the initial direction of light, then you can find what it is at some later time or later space.
But for that we need to, like in this case we know the direction always, that's 45 degree. But in other coordinates we don't know.
Yes. In c equal to 1 units, it's 45 degree. So if what c equal to 1 units means that if you choose c tau and x, then this is 45 degrees. So in Minkowski space time, it was this thing. Sorry to interrupt. Plus say in just x and t dimension, it was this thing, right? And ds squared equal to 0, it means c dt equal to plus minus dx, right? So light would travel like this, either like this. By direction, I mean either in forward or backward. That's what I meant. Obviously, these are independent coordinates, like as you might see. It's just for light, geodesic. Yeah, if you have, this is true in general. If you have n coordinates, in this case 2, a geodesic can be parameterized by just one coordinate here. You just have to give, say, you can give the distance along this trajectory or just some coordinate lambda, which or proper time in some cases. Yeah. Any questions till now? No questions? Feel free to ask me on Teams or yeah. Was it too heavy? Too easy? Medium? What? Please tell.
Like I need to study it again.
Yeah. And like please give feedback. Was it easy, medium, hard?
Sometimes the ds squared equal to 0 path that give us that not by
This thing?
this two that not by
The light wave. Yeah. So okay. Okay. Any other question? This is slightly long explanation. So, any other question? Tong's lecture notes. And okay, I would. How many would come again? Okay. Please be honest. You need not be. If it was too bad, you can tell me. If it was too good, you can tell me. Yeah. Feedback. Give feedback. Don't stay silent. Yeah.
If you go back and say to your friend that the lecture was too complicated, the people are just like fixing their knowledge and all that, and you don't come back again. So we want you to come back again. So tell us what you want in the lectures. What did not work? What worked? Was the pace too fast? Was the content covered too much? Anything. And if you like the lecture, you can also say that.
Yeah. Okay. How many of you liked it? How many of you did not like it? Yeah, that should be the first question always.
This group, don't be shy.
Yeah. Yeah, please create anonymous feedback for. Notes are David Tong's lecture notes. I don't see any. Okay. I have. Yeah, cosmology lecture. So I have created. Cosmology. GR does not talk much about. If you want to see, okay, we have not done any derivation till now, and this was like half of what I had promised. But yeah, it's fine, I guess. You can ask the Astro people to cover the advanced stuff.
S equals to distribution.
What? Sorry.
What is that?
Sorry. What was what?
What is S equals to? That.
This is action. This is capital S. Yeah. This is capital S. Sorry. Yeah. Action is yeah. Oh yeah, same question again. X should be minus. Yeah. It is plus ds squared. Yeah. So thing is, if particle is traveling, no, it should be minus, right? It should be minus. Yeah, because a particle would travel at a speed which is always less than light, right? So this quantity, magnitude of this quantity would dominate over this quantity. T would be more than x. So the ds squared would be negative. Right. Yeah. And the physical distance would be plus with plus ds, but yeah, this point would be with minus ds squared. True. Your point, right? So what we are doing here is we want to study the delay in the time period of a electromagnetic wave. Okay. So should I erase this? Oh, I'll erase this side. This is the exercise. If you are interested, you can do it, or you can just refer Tong's notes. Yeah. So at T naught, I'll just, oh fuck, sorry, I used this. Yeah, at T naught, galaxy at R naught releases a wave, an EM wave, starting at crest number 1. So this, the wave starts at this point. Now it reaches to us at origin. We are sitting at origin, spatial origin. At T1. Okay. So how would we calculate T1? It's by this equation. Okay. I'll call this equation 1. So if you know R, if you know the form of A of t, what is A of t look like as a function of t, you can use this equation to calculate T1, right? Right? Yes. Now, the second, so let the time period of wave be, say, capital T, which in that notation is delta T naught, as seen by the galaxy, or as seen by observer in galaxy, in the distant galaxy. Okay, so it would be, I mean, that event would happen at T naught plus T, which is T naught plus delta T naught, right? Right?
Like for Lorentz relativity of space, d square equals to c square is p square minus d r square. That we get that for light, assuming the speed of light is constant in all frames, we get that d square irrespective of.
True.
And still say for light d square is 0. Or
Yes.
all the other way around.
Yes.
D square is 0 for light, d
Yes.
square is 0.
Yes.
Here, why are we having d square equals to 0 when light is working?
Excellent question. Now we, in SR, we can prove that ds squared is 0 because C is that, I mean, yeah, it's a provable statement essentially. But in GR, I mean, cosmology is just the application of GR. We impose the, I mean, we take motivation from SR and say that ds squared is 0. There is no way to, should I say, prove it. Yeah, there is no way to prove it. Let me think about that. We say that in SR it should happen. Oh yeah, and of course one more thing. General relativity at locally, by locally I mean if you are here and if you do experiments which are close to you, it resembles special relativity. That's the equivalence principle. Yeah, that's the equivalence principle. I mean, there is no way to prove equivalence principle. We believe it holds, but yeah. So if you do experiments near you, so the coordinate changes are infinitesimal, this holds. That's the understanding there. Was that your question? Yeah. I thought, I mean, you did not understand what T0 and delta T1 meant. Yeah. One more question. When should we have the next lecture?
We are planning on 8. Is that right?
It is Sunday night, right? Sunday night. Okay, yeah. Does anyone have a problem? Yeah. Assignments वगैरह कुछ है तो बोल देना. I mean, yeah. Okay, yeah, sure. Thank you. How to turn this off?
You can have speed gradient, speed of light.
Yeah.
How does that happen?
The speed of photon as you measure. Okay, let me be precise.